Good morning, everyone, and welcome to day 3 of the Open Source Summit virtual event. Again, we're sad we couldn't see you in Austin, but we're very happy you could join us virtually today. For those of you who weren't here yesterday, you know that due to technical difficulties, we didn't quite get to see how cloud-native projects power your life in more ways than you realize from our very own Caitlin Raymer. So we're going to give it another try today. Please welcome Caitlin Raymer.
Welcome to Open Source Summit North America. I'm Caitlin Raymer, and I lead business development for CNCF. Today, I'm streaming to you directly from my quarantine kitchen. Being confined to my home over the past few months has sparked much creativity and really got me thinking, where are all of the places that cloud-native projects are powering my life and yours? Do sourdough bread and cloud native have anything in common? Surprisingly, the answer is yes. You just have to know where to look. Enter Pinterest, powered by Kubernetes and letting me realize my inner baker by pinning to my heart's content sourdough bread recipes. Did you know? Over 300 million people visit their platform every month to explore and experience more than 200 billion ideas that have been saved. It's gotta be even more now with this sourdough trend. Today, you'll learn about the benefits Pinterest has seen in adopting Kubernetes and where you can go to get involved and learn more. Let's jump in. One of the main reasons Pinterest chose Kubernetes was because of its flexibility and extensive community support. At peak, Pinterest runs thousands of pods on a few hundred nodes. By moving to Kubernetes, the team was able to build on-demand scaling and new failover policies, in addition to simplifying the overall deployment and management of infrastructure. They had some huge efficiency wins. For instance, the team reclaimed over 80% of capacity of its Jenkins Kubernetes cluster during non-peak hours. But that's not all. Let's hear directly from the Pinterest engineering team on their move to Kubernetes.
Pinterest is the world's first visual discovery engine. Our mission is to help users discover and do things they love. So the scale of infrastructure at Pinterest is pretty enormous. We have tens of thousands of servers, we have 300 petabytes of data, and we have thousands of jobs and workflows that all power the Pinterest experience.
Pinterest has been on the cloud since day one, and it became clear that as the company grew, it was important for us to reduce the overhead of managing virtual machines. Thus, we invested on Kubernetes as the compute infrastructure so we can enable engineers to move fast and remove that overhead of managing machines by themselves. The process involved from all the way evaluating how networking works, to scheduling, to operations, and also community support. We found that Kubernetes definitely aced each one of those areas for us to make a clear decision to move forward with Kubernetes.
Our motivation of joining CNCF was largely because of the community that it gives us access to. We are strong believers in open source software and want to engage and leverage the community to scale the systems that we are using.
How cool was that? I hope this story has left you as inspired as me to learn more about how cloud-native projects are powering your life every day and keeping you connected to the people and activities that you love. Come visit CNCF today at our virtual booth, and don't forget to sign up for KubeCon Cloud Native Con Europe, now virtual, August 17th through the 20th. Let's keep Cloud Native connected and have a great conference. Moment of truth. Whoa. All right, it's perfectly toasted. Check that out.
Thank you, Caitlin. That was some impressive cloud-native sourdough skills. And it's amazing to see that Pinterest runs on Kubernetes. For those of you who have joined us 3 days in a row, you may have noticed my hair got significantly shorter today. My daughter and I did mutual haircuts yesterday, and I believe my daughter was also, my 12-year-old daughter was also inspired by Pinterest for this cut. So We are grateful for all of the great cloud native technology out there that gives us access to tons of information. Our next speaker is going to be talking about another great way that open source technology is powering the world. For the past 20 years, we've seen open source emerge across all sorts of new technologies and capabilities. And open source building blocks have really increasingly become an attractive base for all sorts of new hardware and interesting products. Recently, there's been a trend for safety critical applications to now start considering using open source as well. For those of you who don't know what safety critical is, it's a system where the malfunction could result in one of the following: death or injury to people, loss or severe damage of equipment or property, or environmental harm. So the stakes are high when it comes to safety critical software. Our next speaker is going to look at some of the challenges and approaches to build trust and confidence in open source for use in safety critical software. Please welcome Kate Stewart, Senior Director of Strategic Programs at the Linux Foundation.
Good morning. My name is Kate Stewart, and I'm a director here at the Linux Foundation. And I'm here to tell you a bit more about what we're sort of doing with the safety projects and the projects that have an element of how do we deal with the safety considerations and certifications and making sure open source is safe. I've been around software in various roles for over 30 years now, and been a developer, manager, director, and have looked at various roadmap issues and so forth. And this area is particularly interesting to me. However, as I go through these slides, if you've got any questions, feel free to reach out in the chat or an email, and I will try to answer them as we go. And with that, one of my first memories as a kid was my father pulling me downstairs and pointing out that there was the moon landing happening. And so, I've got this very vivid memory of watching the men land on the moon. And the men would have been landed on the moon without this woman, Margaret Hamilton, who actually programmed the software and did the testing behind the Apollo 11 program. And you can find her source on the internet, and the actual size of the source when it's compiled is much smaller than what we see in IoT devices today. So there's been a lot of change. But the principles that she started and some of the discussions that happened after that revolved around making sure that we had things safe for them. Basically, this slide was taken from IPMI when she gave a keynote in 2018. And that was the first time I saw her live. And that definitely left an impression. And one of the key things in this slide is the fact that they had to have man-made software, and astronauts' lives were at stake, so it had to work the first time. And so this is a very high level of scrutiny and a high level of making sure what we're doing. And so what we've got a lot of methodologies that have evolved since that time to make sure that software is safe to use. And what we're having to look at now is the fact that open source is now the foundation for innovation. And so over 99% of the code bases in 2019 contained open source components from the Black Duck's recent report, double and triple growth in the components. The innovation is coming out of open source. And so we can't ignore anymore how we can use open source in safety critical applications because they're there. We've seen in the last month, we had the SpaceX rockets going up to the space station and the Dragon capsule. The rockets themselves have Linux. The Dragon capsule has Linux in it, and other open source. We also are hearing in the news all the time right now about autonomous driving and the automation of, gas pumps, electric pumps, sensors, signals, so forth. These are all being done and fueled by open source today. And then we also have things, applications coming into the medical space. this is a spreadsheet that shows all of the open source projects that are being looked at for helping with creating an open source ventilator. And so there's source available for all of these projects. They fit the definition of open source. And they have, various constraints, and there's, teams of researchers looking at these and working to advance them. But you can find this whole list of projects out there, and it's all open source. So the innovation that we're seeing in this tremendous rate of innovation is coming from open source. And so at this point in time, open source is already being used in safety critical applications. The challenge right now for us is, how do we actually get it to be safely, how do we basically get that same level of concern and scrutiny put onto it that we had in the past, or how do we basically build up the trust that we can use it safely in these, applications where people's lives are at stake, literally. So at the Linux Foundation, what we're doing right now is we have a variety of projects that are looking towards figuring out how they can go after safety certification. There's a spectrum of them, and so they vary in terms of the footprint size, as well as, how many components they're trying to bring in, what they're trying to do. I'm going to look today at sort of two rough ends of the spectrum. Zephyr is looking at a very, very small footprint for sensors and for, very constrained memory and power devices. And ELISA is Linux, enabling Linux and safety critical applications. And so what we're going to do is take a look at the different approaches. And then there's these other projects like SELT4, Acorn, Zen, civil infrastructure, and automotive grade Linux that are using Linux with components in addition to the Linux, and are trying to make a safe systems as well. So there's a full spectrum that are emerging of projects that you want to use, be used in safety critical environments. And so what we need to figure out is how can we start to tackle this problem. So as people know, I guess Linux has grown into be one of the most important open source projects in the world. So it's a good place to start for your analysis. As of 2019, I think 69% of the embedded systems are actually running Linux today already. And what we've got in the rest of it is, good places for collaboration, because again, these are applications that tend to get used in devices that interact with people, or various machines and so forth, and have elements of safety that have to be considered. So the ELISA project got started at the Linux Foundation in last year in February of 2019. And the key insight for this project is that, to assess if your system is safe, you need to understand your system. Linux as its own code base is, has a lot of history behind it, and has a lot of, pros and cons, and there's a whole bunch of argumentation. It's a tremendously fast-moving code base. But you have to understand your system and how Linux is being used in your system before you can do an assessment. And that's one of the key insights. And so as you understand Linux, there's three different points. You need to sort of understand how to configure Linux, understand the different subsystems of Linux that you're using, and then understand how your system around you is interfacing into Linux. But you have to make sure that Linux is based on what you're needing it to go for, and you're using it in an effective way for the considerations. A lot of the safety standards are basically looking for you to establish guidance on quality and so forth, and they've evolved from a different sort of time and place. What they've been doing, though, is they've come in from a different development model, and Linux has basically been coming in as well for a different development model. And so Linux has been continuously developed for over 30, almost 30 years, 29 anyhow. And there's continuous process improvements in place. There's evidence available already for what the quality processes are and the process improvements, and initial indicators say that we can actually look at getting a reasonable level from the evidence that's there already with Linux. The question is making sure we all consolidate on it and move it forward. So ELISA's mission is to define and maintain a set of elements, processes, and tools that can be incorporated into specific Linux-based safety critical systems to make it amenable to safety certification. This is not a way of actually creating a safe Linux distro. We'll let other people work with that. There's other people who have business cases around that. What we're trying to do is make sure that it is possible to create a system that has Linux in it, that you can make the right argumentation that it's going to be safe for use. And this is what this group is doing. And so we're trying to close the gaps between what's there today and what we need to do. There's a kernel development process working group that's trying to identify safe process reference requirements, and then they assess what's in Linux. You know, what's there today, what testing's happening, what requirements can you extract from your mail lists, things like that. And then there's gaps. So proposing improvements to fill these gaps. There's also a safety architecture working group that's looking to identify the Linux software in terms of chunks, and like memory subsystems, schedulers, things like that, that have roles to play in safety critical argumentation, and then make sure that the appropriate information is in place. What we're looking at is, you know, feeding in from the safety standards worlds what they need to see as evidence, and then upstreaming what we need to the kernel community to help make it easier to satisfy, as well as learning what's happening in the kernel community and bringing that back into the argumentation for systems. And so those are what we're doing right in the kernel. And then what we need to do is prove out that path, what's happening on the outside. And in that sense, we've got a couple of working groups in this one. One's looking at medical devices, one of which is looking at the open source ventilators. Another automotive working group is spinning up, and that's looking at what's happening in the telltales. Pretty much if there's a group of people that want to work on an application, as long as there's source available for it that's not under NDA, we can work with them to sort of spin a group to start having some studies if they have people they want to collaborate with. And the key for this one is that this project is about a collaboration. It is not about engineering your specific systems and so forth. There's limits in this project in the sense that we're not going to be, engineering a system to be safe. We're not going to be creating a safety distro. But we are trying to, and we're not, relieving anyone of their legal obligations or responsibilities, but we're trying to provide a path forward so we can share the effort of coming up with the evidence and the argumentation and build some common understanding in the industry. And so once we have to get to this point where we have some success, we're going to probably have these assets available for the processes and the features and, next level of information down. We should have some reference systems from those use cases. And we should also have built up the knowledge in the open source community a lot further. Right now, there's a lot of knowledge about what we have to do with security. And we kind of need to get to the same level of knowledge in the kernel community about safety and dependability. And so, and this ties in nicely with existing testing efforts. So we'll be continuing to build on that and extend from there. But that's what the ELISA project is looking at right now. And, our upstream here is the kernel community itself and the Linux kernel. So getting up, improving the documentations, improving the testing, and, making the evidence more accessible, the bugs more accessible. These are all things that we need to do in order to build up the argumentation for safety. So that's sort of one approach, which is, quite different when you think of from a traditional certification. But this is pretty much how we're going to have to look at getting Linux to work effectively. If you are interested in learning more, we have virtual workshops right now in these current times, and we'll be scheduling one in July. We'll be put the schedule out in July for when we're going to be having it, probably in August or September. It's still being discussed. And there's our links to our website and the mail lists and their sources. And so if you've got any information, please join the mail lists and start asking questions or join in some of the meetings. The other project I want to chat about is on the complete other side of the spectrum. And this is Zephyr, which is another OS. It's been designed as a project to be used when Linux is just too small. Linux is too big. And so Linux right now doesn't get below 2 meg. And so Zephyr is sort of like, 8K to 512K type of space. And you just compile in exactly what you need. And you have a very limited stack and a fairly good amount of functionality. It started in 2016, and it was literally designed as an open source project. to be an RTOS kernel, and it was built with safety and security in mind. Literally right from the start, we pretty much knew we were going to go after the safety as a goal with this project. And so we have a community that is acceptable to making coding, coding style changes and doing things in a fashion that's more appropriate, I guess, or more familiar to the safety assessors. And so this project is going to be going after certification as well. And it's going after 61508. And so what we're doing with this one is looking towards putting the right pieces in place and then working with assessors directly to make sure that we have a reference system and available for people to use as models. We're working with assessors in the ELISA project as well, and they're active participants in the groups. So we're getting that set of inputs. We've got inputs from the safety community, the assessors. We've got the developers participating, and then we've got management and business people. And so these are all necessary to have a good discussion and figure out a pragmatic solution here. In Zephyr, right from the development, we've been looking at quality as pretty much a mandatory requirement. There's various code scanning that's going on already. We're using Cochinelle, like the Linux kernel is, for doing some of the interfaces and checking the interfaces and trying to find bugs that way. We're also trying to use Coverity like the kernel does. Both projects are sort of looking at running automation, and then we're looking at a variety of other static analysis tools to apply here. And we're actually formally moving the code base over to be MISRA compliant, because that's pretty much what the safety assessors expect. And so there's a whole set of coding guidelines that the TSC has been working on and are being deployed this year. The Linux, Zephyr itself, though, is actually a pretty complete stack at this point now. It's highly configurable, it's modular, it's using the device tree like the kernel does, it's using kconfig for figuring out what options are being used and what you're compiling together. And as you can sort of see, it has a pretty complete stack. What we're trying to do in this case, though, is we're going to be starting with a subset and then building our way out. And this is how we're going to try to control the change rates. In terms of the code repositories, Zephyr has a development tree, and that's where all the development is happening. We're sort of getting close to about 2 commits an hour there now. For comparison, the Linux kernel is about 9 commits per hour into their upstream. But every 2 years, we're cutting an LTS, or long-term support. And from that, we're taking a subset of the modules, and those are what we're going to be taking and working through the argumentation for safety certification. And in this way, we're trying to balance the change that has to happen so quick in the upstream to keep the community interested and engaged versus what we have to do to sort of hone in the argumentation and be able to take it through a more formal audit. The auditable branch that's there right now is based on a subset of the kernel's modules, and we've got the safety and security committees both looking at it and talking about it with the TSC before it moves forward. And the actual subset that we're looking at for 61508 right now, which is our first target for Zephyr, is illustrated here in blue. And so we're looking at some of the key interfaces. And we're basically working our way forward with that, getting these components the right level of traceability requirements, following the V model, and doing things in a more way that the safety people are expecting to see the evidence. And so for Zephyr's roadmap, we're sort of looking right now, we're working on getting that MISRA code base, and we're getting the coding guidelines adapted. One of our members is working on an accelerated path of taking one of their products through. And next year, when we come out with our next LTS, we expect to be able to take that one through getting the certification. So we start working with the certification authorities right now on this one and are busy working our plans up for that portion. So that's kind of what we're doing with Zephyr. And if you're interested in learning more about Zephyr, you can sort of find the information on these various, most of the code's on GitHub. There's various websites and mail lists for this project, as well as we have a very active Slack channel. So if you have any interest, by all means, you're welcome to come in and participate. And then, just want to quickly give you a summary. Oops, hello. You know, I think we have pretty strong evidence we've got to figure out how to make it coexist. We need to figure out how to make open source and the safety certifications exist at scale so people can have the confidence that they can depend on the code and trust it. We need to basically start looking at getting this quality at the project level, at the open source project level, because once you get these people creating products and integrating everything together, they're depending on these open source components. And so we need to make sure that they have good foundations to build off of. And then the other thing we're going to have to be working on is managing the developer and the certification authority expectations as we're working with this. Certainly the certification authority guys are looking at this and trying to figure out, okay, how do we deal with this open source? And the development community needs to understand that some of these pieces of evidence and testing have reasons behind them, and how do we basically make it efficient for everyone? How can we automate as much of this as we can so that we can all move forward together? So these are the sorts of, you know, a little sample of what those two ends of the spectrum are like, and there's a lot of different approaches that are variants of these things in that middle portion of the project. So there's a lot of different approaches being taken, and I guess we'll see in about a year's time where we're going and which ones are out there. And with that, I'd just like to say thank you very much. And if you want more information about these projects, the links are here, or feel free to contact me by email or by chat. And thank you.
Thanks, Kate. And again, if you have any questions, feel free to submit them to Kate in the chat. And we really, it's nice to see the intersection of standards, safety critical guidelines, open source, all now coming together and reaching a state of maturity that they can be used in mission critical systems, automotive devices, medical devices, and so forth. So thank you, Kate, for all of your great work. Our next speaker is Alan Clark, the CTO of Industry Initiatives and Emerging Standards at SUSE. Today's global headlines are definitely changing the way we do business, and that change is being reflected in the manner in which modern software is being defined, distributed, and deployed. Alan will discuss the keys to this transformation. Please welcome Alan Clark.
Hello, my name is Alan Clark, and I'm a member of the SUSE CTO office. You've heard today a lot of global headlines being mentioned in the sessions that we've listened to. Today's global headlines are truly driving a change in the way we do business. And that change is being reflected in the manner in which modern software is being defined, developed, distributed, and deployed. In today's world, software is truly transforming today's business infrastructure. There are three keys to be successful in this transformation: simplify, modernize, and accelerate. In just a couple minutes we have, let's highlight how recent technologies are crucial to these three transformational keys. Note that every company is built on subtype of advantage: discovered inefficiencies, unfulfilled market desires, or regulatory mandates. Lasting companies are built on structural advantages. However, sometimes our myopic views limit us from seeing our own company's IT structural weaknesses. For example, a report through SUSE states that 75% of businesses consider themselves to be customer-centric, while only 30% of customers believe that businesses are customer-centric. Perhaps you've seen this yourself. Non-response or disruption is a key contributor to customer perception of a company being non-customer-centric. The report also notes that 1 in 3 companies have reported at least one disaster or a significant disruption during the last 5 years, of which they were caused by hardware failures, software failures, telecom failures, data corruption, failed upgrades, or human error. Global events such as COVID-19 are forcing companies to rapidly modify their future plans and to deploy solutions today as a rapid response to changes such as social distancing and touchless contact. It's easy to get caught up with the immediate, deploying siloed point solutions to rapidly demonstrate quick response. It's very tempting to do such rollouts given today's pressures. But a quick short-term success could be the beginnings of a long-term IT headache and an unsure foundation for the business. Building silos quickly becomes untenable and complex. Such complexity builds unreliability, hence leading to customer dissatisfaction. But quick does not have to be unsure. A solid architectural advantage starts with a solid foundation. With today's modern rapid application development and deployment platforms, rapid doesn't have to be fragile or insecure. You can deploy apps in a simple fashion on modern architectures. The key is to build on top of a foundation that enables simplicity, modernization, and acceleration. SUSE's vision is to be the most innovative, trusted leader in providing open source solutions and technologies for the enterprise to simplify, modernize, and accelerate traditional and cloud-native applications across the IT landscape in any environment. This vision is built on a solid foundation with over 25 years of experience and knowledge for delivering enterprise-ready, secure, and trusted open source solutions that enable developers, 1, to rapidly create and accelerate delivery, 2, leverage modern container-based platforms, and 3, use tools such as artificial intelligence. And for the operators to deploy such solutions across their domains in patterns that will provide their customer a robust and a reliable experience. This implies that solutions can and will extend from the edge to the core and to the cloud. Operators can and want to manage workloads where and how it makes sense, including leveraging different architectures, but with a common code base. This enables developers to take advantage of features such as vGPUs, high-power CPUs, or very secure I/O. It also leverages consistency across the architectures. How does this impact being customer-centric? Consider what this means in terms of customer response. Downtime reduces customer response. Reboot cycles are very long in a customer's eyes. This means that uptimes are paramount, but response to vulnerabilities are just as critical. Do these conflict? Not today. With powerful technologies such as live patching, IT can patch the vulnerabilities without incurring downtime. But the key point here is consistency across the architectures, which means that this capability needs to be available on all architectures, and that's true today. For example, SLE now deploys live patching on the Z platform. As you are well aware, the growth of open source is growing exponentially today. But consuming open source can be cumbersome. But through SUSE's Package Hub, popular community open source software is pre-built and ready for use, not just for community Linux distributions, but also for your enterprise distributions, such as SUSE Linux Enterprise. Package Hub is where the enterprise meets the community. For the enterprise users, community packages are available for SUSE Linux Enterprise. Enterprise users now participate in community's open source innovation, and it provides them easy access to standard open source tools. For community users, it means that they have access to over 9,000 community packages that are maintained and supported by the community. These community-maintained, factory-built, high-quality, up-to-date, latest technologies, up-to-date packages are built by the OpenSUSE community for community use and for use on community distributions such as OpenSUSE Tumbleweed and OpenSUSE Leap. It's very easy to move from community to enterprise. In-place migration from SUSE Leap to for example, SUSE Linux Enterprise. This means that it's now DevOps friendly. Development and projects can use the community distribution, while operations can run in an enterprise environment. So to summarize, what I've quickly conveyed is that every company, your company, is built on some type of advantage. Lasting companies are built on structural advantages. The key is to build that advantage on a foundation that enables simplicity, modernization, and acceleration. Thank you.
Thank you, Alan. Great talk. And now we've got 4 great lightning talks, starting with a talk about the Wyliodrin Studio. Please welcome Ioana, Culic, Cosmin, Radu, teaching assistants at Politehnica University in Bucharest.
Hello, and thank you, Jim, for the introduction. So today we are going to talk about Wyliodrin Studio, a platform that helps you build IoT prototypes and turn them into small-scale deployments. To start with some quick words about us, we are Ioana and Cosmin. I am a teaching assistant at the Politehnica University of Bucharest and currently a PhD candidate there. And I've been working with IoT technologies for the last 7 years. Cosmin is my student, and he has been building IoT applications during the last 3 years, Wyliodrin Studio being one of these applications. A little bit about the context. So we are all aware that objects around us are becoming smart. We have our refrigerators or our vacuum cleaners connected to the internet and running software. And in this context, we have fields such as automotive or mechanics relying more and more on applications being built and on software being deployed. And what is more, these applications are usually not built by computer scientists and computer engineers, but by specialists in that specific domains. As a result, there is a need for tools especially designed for these people who are not very into computers. And we have the Arduino as a very good example. The Arduino aims to be a prototyping device that targets people who are not computer specialists. And as we can all see, it really succeeded in doing this. However, the Arduino has some limitations. And this is why in many of the IoT devices nowadays, we can find Raspberry Pi or Raspberry Pi-like devices. These are actually computers. And they are really easy to use when you use them as computers, when you connect them to a screen or to a keyboard. But things can get a bit trickier when you connect them inside the robot or place them on top of a building. In this case, usually what we would do is to connect remotely to it, either via SSH, and we would have like a shell interface, which is not very intuitive, and run some commands. And when it comes to actually deploying code on the device, things can get even more trickier. And while for people who are really into computers and into programming, this can be just fun and another challenge. If we think about students or persons who just want to build some fine arts projects or just control some mechanical stuff, this can get really intimidating and will stop them from actually building the products that they aim to build. As a result, we created Wyliodrin Studio, a small project that aims to help both experienced and non-experienced people in building IoT applications. And further on, I will let Cosmin describe the interface a bit.
Yes, the interface is pretty simple. You have the main file where you can write the code that you want to run on a device and a couple of configuration options. However, our aim is to keep it intuitive and don't get user in plenty of configurations. Local devices can connect to the platform either by a serial connection or via the network. When you hit the connect button, the application will scan the network and do USB ports for all the connected devices. In addition, you can connect to a remote device via the internet. For this, Wyliodrin Studio will generate a connection token that you need to copy in the device's memory. To run the application, you just need to hit the run button and Wyliodrin Studio will deploy the source code on the device and launch it. Wyliodrin Studio is available in several languages, and of course we are looking for translators to make it even more accessible. This is especially for young users who are more comfortable with an application that is in their mother tongue. For advanced users, we have a project tree that which will help them to build multiple file applications. This enables them to manage complex projects with modules and external functions. They can also generate a custom makefile, so they can describe how the application should start. Basically, when they will hit the run button, Wyliodrin Studio will run the make run command, so they can customize how the process would be. They also have direct access to the device via a shell. We also implemented the device simulator, so users can run a very simple application without an actual device. This is to help them to test some very basic functions. Besides the simulator, we also implemented a Raspberry Pi OS emulator using QEMU. This allows you to run more complex applications using only your personal computer. Now that we have talked about the prototyping part, at a certain point you need to take your projects further and deploy them as products that others can also use. The Arduino team is taking the first steps towards this direction by launching Arduino Pro, and so did we. We added the capability to build stable applications that can be deployed on multiple devices. We did this using containers. So when you create your project, you have the option to edit the Docker file and customize the way that your application will start. When you hit deploy, the code is copied on the device and the container image is created and launched. If the device is reboots or if the application crashes, it will automatically restart.
Okay, so here we have some of our users. Most of them are educational institutions in Europe and in US. And a little bit about the technical implementation. The platform relies on plugins, so it's very easy to extend and anybody can bring new functionalities without having to interfere with the previous code base. We currently have plugins for most of the functionalities presented before. We can see the supported programming languages, for instance. We have Python, Node.js, Shell, and the visual programming environment, which is actually based on Google Blockly. Besides being an easy-to-use IDE, Wyliodrin Studio doesn't store any user data, so in Europe this means that it's GDPR compliant. And in regards to the devices that we support, Wyliodrin Studio is compatible with the Raspberry Pi, the BeagleBone Black, and NXP's Rapid IoT Prototyping Kit. And here we would like to thank NXP for their support. They have helped us a lot in integrating this device, and they also offer some scholarships for our students so they can work on this. The platform comes in two flavors. You can either use it as a desktop application or in a browser. In both cases, the platform doesn't store any user data. All the data required is stored on your computer. It's open source, as we mentioned before. The license is Apache 2.0, so we would like to invite everybody to contribute to the platform. You can see here me and Cosmin, but actually we are a team of around 10 people working on it, and we would like others to join us. The platform is written in JavaScript and it runs on top of Electron, so it doesn't use very difficult technologies. And as I've said, we are looking for contributors, and we would also like to have more people translating the platform, so it becomes even more accessible. You can find us on our website, wyliodrin.studio, and on GitHub. And we've also just recently published a book together with A-Press. It's not on the slides as it is really recent, but you can find it on our website. And with that being said, we would like to thank you for the attention, and we will take any questions in the chat.
Thank you, Ioana and Cosmin. That's really great work that you're doing, and I really encourage everyone to ask questions in the chat, but more importantly, go to the Wyliodrin Studio website, go to the GitHub repos, and check it out. What an amazing project. Nicely done.
Thank you.
Thanks. Next, we have a talk on OpenBMC and migrating inside the box communications from IPMI to PLDM. Please welcome Deepak Kodihalli, Senior Engineer at IBM.
Hello, everyone. My name is Deepak. I work with IBM in Bangalore, India. I'm with the IBM Systems Group, and I primarily write open source firmware for the baseboard management controller, or the BMC. This is my first experience at the Open Source Summit, so I'm excited to be presenting here. I've presented at other open source conferences, but this is also my first virtual one, so that makes it interesting. Over the next 5 or so minutes, I will talk about inside the box or inside the server communication protocols, and how and why we are migrating those on some of the upcoming IBM servers from a protocol called IPMI to a protocol called PLDM. My talk today is in the context of OpenBMC, so I'd like to introduce that first. A BMC is basically a small computer which sits within a bigger computer. You would typically find it on the motherboards of servers. The BMC enables various management functions, such as powering on the server hardware, monitoring the health of the server in terms of reading temperatures and voltages, capturing debug logs, providing interfaces for remote management clients, and so on. So the BMC actually has great control and power. And with great power comes great responsibility. But unfortunately, that's been a bit hard to achieve with traditional BMC firmware stacks that have always been closed sourced. That poses problems in the areas of security, tooling, and customizing the BMC stack. So these are some of the problems that OpenBMC is trying to address. So basically, OpenBMC is a Linux Foundation project. It is a Linux-based distribution for BMCs. There are several companies today that either design or build systems, and they're adopting OpenBMC as well as contributing to OpenBMC. Moving on to the next slide. On this slide, I'd like to introduce the term inside the box communication. So typically in servers, the baseboard management controller, or the BMC, is involved in a lot of talking. As you can see in the picture, the BMC can talk to the platform server software. The BMC can talk to other BMCs. The BMC can also talk to connected devices, for example, PCIe devices or sensor chips and so on. And all of these inside the box communication paths are for enabling use cases such as state control, power control, exchanging monitoring and health information, exchanging through information, and so on. So this basically means there are different firmware stacks that are trying to talk to each other over different physical buses. Now, if these firmware stacks would use proprietary protocols, that would mean, for example, the BMC firmware has to change over and over again when the host firmware implementation changes, or the device firmware implementation changes, or if there are newer revisions in those firmware implementations or devices. So that kind of makes it necessary to go for industry standard communication protocols, so that all of the boxes here are kind of talking the same language. Let's move on to the next slide and look at one such industry standard protocol, which is IPMI. Now, IPMI is a pretty old protocol. It's pretty popular as well. It's used for inside the box communication. It's also used for out of band or over the network communications to talk to the BMC. As shown in the picture here, on certain IBM servers, we've tried to use IPMI as the communication protocol between the host firmware and the BMC. While that works okay for small servers, it doesn't scale really well for enterprise class servers because there are some inherent limitations with the IPMI specification. For example, the IPMI specification reserves a single unsigned byte for a sensor. That would mean you can have at most 255 sensors. On large-scale enterprise servers, just the number of memory modules, for example, could exhaust the IPMI sensor space. There are other limitations. The IPMI specification talks about the messaging protocol as well as hardware channels, and there's a bit of coupling between them. It's hard to design the messaging protocol and the hardware channels separately. Examples of the IPMI hardware channels are KCS and BT. BT stands for block transfer. The hardware channels have their own limitations. They're not really performant, for example. So if you were to update firmware in band, and let's say the firmware image is 32 megs, if that happens over IPMI packets, that could take hours. Finally, the IPMI spec is currently not under active development. So there's basically a need to find inside the box communication protocols that address the limitations that I spoke about. But at the same time, we don't want to implement proprietary ones because, again, then there are issues in terms of interoperability. This is where PMCI comes into picture. So PMCI is a DMTF work group that comes up with standards to enable inside-the-box communications. As you can see in the picture here, PMCI covers various forms of inside-the-box communications, the BMC talking to the platform software or the host firmware, the BMC talking to other BMCs, talking to the network card or managed devices, and so on. So PMCI is a collection of specifications. A couple that I want to call out in the context of this talk are PLDM and MCTP. PLDM stands for Platform Level Data Model. It's basically a data model and a set of messages that enables exchange of information such as monitoring, health, through, and so on. MCTP is a transport protocol. MCTP stands for Management Control Transport Protocol. PLDM typically runs on top of MCTP. Together, these protocols address the limitations of IPMI that we spoke about previously. Moving on to the next slide. So this picture represents the full PMCI stack. As you can see, this is layered. There are 3 layers: a physical layer, a transport layer, and upper layer protocols. The physical layer comprises of well-known physical inside-the-box interconnects or buses, for example, SMBus, PCIe, serial. There are a couple of transport layer protocols, MCTP, and also one called RBT. And there are several upper layer protocols that run on top of these transport layer protocols. PLDM is one of them. The goal here is to enable the transport and upper layer protocols to be designed separately without causing a coupling. And the goal is also to be able to make it easy to introduce newer physical buses, newer transport protocols, and upper layer protocols. One of the ways in which this is achieved is, for example, with MCTP. The MCTP base protocol is agnostic of the underlying physical buses. That is achieved by companion binding specifications. For example, you can see an MCTP over PCIe and an MCTP over SMBus binding specification. Also, as you can see here on the top, PLDM itself is a collection of specifications. Each of them tackle a specific function. Moving on to the next slide. So next, let's look at what's happening on OpenBMC in terms of MCTP and PLDM and how these protocols are helping us solve some of the challenges that we faced with IPMI. So first of all, OpenBMC has an open source PLDM and MCTP stack. There are parts of those, namely libPLDM and libMCTP, that are platform agnostic. They contain all of the protocol-specific API and implementation, and they can run outside of OpenBMC as well. For example, the host firmware stack on IBM systems makes use of libPLDM and libMCTP. As you can see in the picture here, what we've done on OpenBMC is we've implemented the MCTP base specification and the PLDM base specification. There is implementation for some of the binding specs as well. For example, the PCI binding specification, there's a serial MCTP over serial binding spec implementation. It is also possible to throw in vendor-defined bindings into the picture. For example, we have one for LPC. At the same time, it's also possible to standardize them by proposing the same to PMCI. PMCI has a very active work group that works on spec development and enhancements. Also, as you can see, PLDM profiles or the individual PLDM specifications in the areas of BIOS settings, monitoring and control through information exchange are being implemented. Another important point to note is PLDM scales much better than IPMI. For example, PLDM has 2 byte sensors, so we don't have the limitations of IPMI. Moving on to the next slide. So I'll basically end with this slide. What I have here are pointers to some of the PMCI documents and also pointers to the OpenBMC source code and design docs for PLDM and MCTP. That's it. Thanks much.
Thank you very much. Our next speaker is Daniel Qian, software engineer at eBay, and he joins us to talk about unified cloud infrastructure remediation at eBay. Please welcome Daniel Qian.
Hello everyone, welcome to my session. I'm Daniel Qian from eBay Infra team. I'm going to talk about how we modeling eBay cloud infrastructure and how we building the unified cloud infrastructure remediation system. This is my agenda. I will first introduce the eBay Kubernetes footprint, and then how we manage cloud infrastructure with the Kubernetes capabilities. And based on these models, we build a unified cloud infrastructure remediation system. First, eBay started Kubernetes in 2015. We running the internal distribution named Test.io. As of now, we already have over 80 clusters running in different VPCs and environments. There are multiple 2,000 plus size clusters with heavy workloads. The various production workloads, including the web frontend, databases, search engine, Hadoop, and machine learning. And we are also running on the edge for a better end-user experience. Okay, now, after getting some ideas on eBay Kubernetes footprint, you may be wondering how we get there. The short answer is we use the Kubernetes to manage the cloud infrastructure lifecycle. At first, in order to manage them in Kubernetes way, we modeling all the concepts in infrastructure layer and the software layer, from the AZ, RAG, compiler set, VPC, to STU, flavor, OS images, node pool, and compute node. All these models can present everything we need to do like node provisioning, Kubernetes cluster build-out, and the key optimization, the node remediation. So, after we have the multiple models, we can have a look about how we use them. Here is the architecture view of over one single AZ. Let's go through it quickly. At first is our control plane. It has the API server, etcd, and all of our controllers, named testmaster. Then we have some pre-created objects like OS image and flavor, which contains the OS tree and the dist partition specs. After we have these objects, Let's say we have a rack from our data center. We can generate all infrastructure layer models like asset, L2 domain, subnet, and even the route from our eBay CMDB. Once you have the assets, and they can be consumed by our homegrown provision system to be a compute node. And after we have several provisioned compute nodes, we can leverage the sort state to build Kubernetes clusters with the DataOps way. Okay, now we already know how we provision host and build the clusters in eBay. And since the system and the hardware can fail, so a unified and highly automated remediation system is needed for the infrastructure lifecycle management. Here is our unified remediation framework. There are 3 layers, and I will introduce them one by one. The first layer is a detector. This is of our eyes to find out the node failures. Currently, the most important 3 kinds of detector for us is node prompt detector, Leibniz readings probe, and alert detector. The node prompt detector is an open source project in Kubernetes. It provides a flexible framework for us to leverage different tools and alerts to detect hardware failures like MC error, IPMI error, and dist error. Then for software layer failures, we leverage the Leibniz and the readings probe to detect the key components of our system, like the node prompt detector itself and the host runtime. The last but not least is the alert detector. It will be used to find out the other failures from our monitoring system. Then we already have the classified node failures. We can leverage the remediation framework to configure different remediation policy for different of failures. Here is some kinds of node failures we already have classified. You can see in the hardware failure part, we can have multiple subcategories like the MC error and the dist error. And further, we can even know whether this is a dist lost or a dist read-write failure. And based on the fine-grained categories, we have the customized remediation policy for each of them. Each remediation policy consists of one or multiple remediation actions. The actions can be 2 parts. The first one is on failure actions, which will be triggered when we detect the node failure. We can restart, reimage, reclaim, or trigger fixed asset on the unhealthy nodes. After the on failure actions bring the nodes back to healthy, we can have used the on success actions to restore data or send some notification to us or our customers. Okay, after we have the view of the unified remediation framework, we can have the example of how the remediation flow works. Here is the node probe failure remediation flow. You can see it has the highest priority, and after the precondition matches, the on failure actions will be treated one by one. Of course, if the node becomes healthy again after several actions, the left ones will be skipped. At last, the on success actions will be triggered to do some automated operations. The previous flow is the generic remediation flow, but we know some applications are not stateless. So in order to not affect the running workloads and give them time to do like the data migration or failover process, we suggest the operation owners to leverage the Kubernetes concept, the pod disruption budget. Application owners can use the pod disruption budget to hold our remediation flow. And if the grace period in the policy has expired, we will kick off a workflow to ask the application owners to complete the migration and or failure over process as soon as possible, and then to remove or change the pod disruption budget to continue the next remediation flow. Okay, that is all what I want to share today. And if you are interested about this topic, you can reach me to have a further discussion. Next is the Q&A part. It's your time. Thank you.
Thank you, Daniel. Finally, we have Joel Lehman, Senior Research Scientist at Uber, joining us for a lightning talk on an open source model, ZOO for analyzing, visualizing, comparing deep reinforcement learning agents. Please welcome Joel Lehman.
Thanks, Jim. It's a pleasure to be here. So to give a 50,000-foot view of what this talk is about, I'll be talking about a project that aims to make it easier to do a particular kind of research. We want to make it easier to research the behavior of reinforcement learning agents produced by different algorithms. I'm going to dive into this more clearly so you get a sense of what I mean, but we want to be able to basically understand reinforcement learning agents better than we do right now. And so I'm going to use the title of the talk as a device just to kind of illuminate the different terms within it so we can build up to an understanding of what this project's all about. So this project is about deep reinforcement learning agents. So this is a paradigm of machine learning in which you're trying to train an agent to take actions in the world such that it gets high rewards. And to make this more clear, we can talk about a specific domain. And it's the domain that this project focuses on, which is the Atari reinforcement learning benchmark domain. So this is inspired or builds upon the Atari 2600 video game console, which some of you may be familiar with or have played. And this console can now be emulated within a computer, and it just provides a wide range of simple and yet sometimes difficult challenges for reinforcement learning agents to learn. So the agents in these environments will be trying to take actions, basically press buttons in the games from viewing the pixels of the video game and trying to make the video game score go up. So that's the Atari part. This is sort of the domain that a lot of what I'll be talking about will be taking place within. And then what's a model zoo? So a model zoo is describing a place where you can store trained models. So it might seem a little bit wasteful, but what people usually do when they're training big machine learning models, particularly in reinforcement learning, is you'll train a model from scratch, and it could be a very big model, many millions of parameters. It could take a lot of effort to train that model. It takes a lot of hours on a GPU and CPU as well. And then after you train this model, you might just take the trained weights and throw them away and just look at the score that you got, like how many points in Atari did you get. But if you have a model zoo where you can upload models and compare models to other people's models, then it can actually make analyzing the behaviors a lot easier. And that's exactly what we want to do, is to help us to better understand what these big neural network Atari models are actually learning. And so what's shown here is an image from analyzing a image classification network, so not reinforcement learning, but showing ways to visualize what each neuron in the network is learning. And it's a way to understand why it's making the decisions that it's making. And we might want something similar for deep reinforcement learning. So just to dive into reinforcement learning, just to make it a little more concrete. So on the left, we have this game Breakout, where you're trying to control the paddle on the bottom, and you're trying to destroy all the blocks, and that means with the ball. So this is like an agent that isn't very good. So it hits one block and then it dies. So it gets a score of 1. And you can imagine there would be ways to improve upon this agent. The agent might somehow get more rewards just by hitting the ball off the paddle by chance. And eventually, through a lot of feedback and trying new actions, it could get very good. This is showing an agent that gets 335 points. So in reinforcement learning, again, the agent is just trying to learn how to get the highest score. And people are really excited about a form of reinforcement learning called deep reinforcement learning, which just means using deep neural networks, as a way to encode a policy that can learn how to play the game. So there's been a lot of success in deep reinforcement learning. It plays Atari well. It's become world champion in Go. There's examples of using robots to manipulate Rubik's Cubes. And there's a lot of potential here because many tasks that we care about that have economic or social value can be framed in terms of an agent like a robot doing something in the world. But this potential hasn't really been met commercially as much as in supervised learning, with all the image recognition networks, for example, that have had a lot of commercial impact. I think one of the reasons that deep reinforcement learning hasn't had this impact, although there's many reasons, one is that it is really critical if you have an agent doing things in the world to understand why it's doing what it's doing, to make sure it's not exploiting some sort of trivial edge case that's not going to malfunction horribly if you go a little bit outside the training distribution. So just as explainable AI is important for supervised learning, it's also important for reinforcement learning. And this project is about trying to make interpretability of and understanding of deep reinforcement learning agents easier. So this is kind of coming back to the headline I mentioned earlier. And just a little backstory is that we came upon this project because we did some work with evolutionary algorithms, training them on Atari, and we wanted to compare these agents to the agents that were kind of created by more traditional RL agents. And when we embarked upon that journey, it turned out it was really hard. And so like this kind of was born out of just a personal desire to do something, and finding it so hard to do it. You have to like retrain agents, you have to kind of figure out all these different code bases for all these different RL algorithms, and it takes a lot of work and it's really annoying. But with the software we've created, it makes it a lot easier. So now you can just say, I want to download the model for the algorithm A2C that was trained on Sequest, a particular Atari game, and then I want to grab the frames of animation to see what the agent was doing. I want to get the representations to understand how, from a high level, the neural network was seeing the world, and you just kind of plot them. And so that gives us sort of what the Atari Zoo project is, which is just a lot of trained models. In some ways, this is another form of open source where you're just releasing not only the code, but the trained models that are the code plus data and so on. And so we release trained models across all the different games at Atari, trained in all the different RL algorithms across different independent runs. So a lot of data, and then also accompanying software that can help to analyze that data. And I want to note that we build on 2 previous libraries. A beautiful aspect of open source is being able to build on each other's projects, and our project is also open source. But Lucid and Dopamine are 2 cool projects that we found useful. And now I'll just talk about some things you can do with this model zoo and why it's interesting. So one thing is you can just quickly create a lot of videos where you can just qualitatively glance at the different kinds of things that different algorithms are learning. So here we have 3 independent runs of 3 RL algorithms trained on Sequest. And these policy search algorithms, the ones that are highlighted in green, are all finding the same local sort of degenerate behavior, just going to the bottom of the ocean and just sitting there, whereas the other RL algorithms are finding more sophisticated policy. So you can quickly identify this pathology. You can also look at the internals of the neural networks and understand something about the brains that these different agents are creating. So this is once again in Sequest and just comparing sort of some of the early layers of these neural networks to each other. And the non-evolutionary algorithm methods are finding what are called filters that have a lot more structure than the evolutionary ones. Again, hinting that the evolutionary ones are doing something different, maybe a little bit more superficial than the other algorithms. And similarly, if we look at how much attention different algorithms are paying to the present versus the past, something you could do by looking at their brains, the first layers of their brains, then we find again that evolutionary algorithms are different. So just kind of some initial validation that we can use this data set to make interesting discoveries about how different kinds of algorithms are the same or different. You can also kind of like test these trained agents in different scenarios to see how robust they are, to see if they break, which algorithms are more likely to break. And one way to do this is to sort of add fog to their inputs, to add more noise to their inputs, to see if that added fog causes them to fail. And one thing we discovered was that the what are called policy search algorithms were more robust to this kind of fog than were the value-based reinforcement learning algorithms, just 2 different classes of RL algorithms. And the final thing you can do is have some neuroscience almost, where you can visualize the activity of the brain, which is on the right, along with the agent acting in the world. And you can make some interesting discoveries. So if we zoom in to just one neuron of this brain, this is sort of in the later layers of the neural network, we see that it's actually found a neuron that tracks the sub. It's kind of an interesting discovery. And there's a web tool that you can look at where you yourself could explore these sorts of activation patterns and see if you can find other kind of interesting neurons. So to close, there's a lot of things we might hope to do. Might hope to expand beyond Atari and look at other more real-world domains. We might add more analysis and metrics. I just want to end with the idea that maybe there's some really interesting discoveries that are being waiting to find in this big data set by both professional researchers and citizen scientists. So I hope that you will check out our project. There's all these co-authors who contributed to this work, some at Google AI, some at OpenAI. Here's their pictures. And to conclude, feel free to send me messages through the conference chat or message system. Really excited to see how people use this and looking forward to talking with you. So thank you very much.
Thank you very much, Joel. I would love to see your algorithm applied to find the Easter egg in the 1980 adventure game from Atari. But really interesting stuff. Go check out their website if you would like to see more. Our next speaker is Krste Asanovic, chairman of the RISC-V Foundation, chief architect and co-founder of Sci-Fi, and a professor in the Department of Electronic Engineering and Computer Science at UC Berkeley, where he also leads the free RISC-V ISA project. The most important interface in a computing system is the instruction set architecture, as it connects software to hardware. Today, Krste will discuss the RISC-V project, which provides a free and open alternative to proprietary instruction sets, with the promise of opening up the hardware world to the same kind of rapid innovation seen with open source software. Please welcome Krste.
Hi, thanks, Jim, for the introduction. Really excited to be here at to talk at this open source event, open source software event about our project on open source hardware. So RISC-V is an instruction set, and the motto is that instruction sets want to be free. But first, I think it's kind of useful to kind of explain to people why instruction set architecture actually matters, why are ISAs important. And the way I like to answer this question is by asking some questions. Why can't Intel sell mobile chips? They're a big, powerful semiconductor company. How come they're not in mobile chips everywhere? And the answer is pretty simple, is that most of the mobile phone tablet software requires an ARM-based ISA. And so almost universally, you need a ARM-based ISA to run any mobile software. Conversely, why is ARM partners having a hard time selling servers? And the answer is most server systems expect to be running on actually an AMD 64 ISA. A side question that might raise is, how come Intel is making all this money selling servers based on an AMD designed ISA? And the history of that is that Intel actually tried to move the whole industry over to a different ISA, Itanium. Thankfully, they failed now, but Intel is still doing quite well selling machines based on this AMD designed ISA. Finally, how can IBM still sell mainframes? So if you look at the IBM Z series, it can trace its roots back to the IBM 360, which is the oldest surviving ISA. Over 50 years now, this ISA has been in existence. And actually, the 360, when it was introduced, actually also introduced the notion of an instruction set architecture, the idea that you should separate the software interface to a hardware platform from the actual implementation of that platform. So the instruction set is really the most important interface in a computer system because it's where software meets hardware. So in the rest of the computing, we have open interfaces. So if you look at networking with Ethernet, operating systems with POSIX, languages like C, databases, we have SQL, graphics, OpenGL. We have open standard interfaces all throughout our industry, but we haven't had that at the instruction set level. So why is that? Why are we being stuck on proprietary owned interfaces, x86, ARM, IBM 360? We think there's no good reason, and that's part of the premise of the RISC-V project, is we should have an open interface there. Now, you may say, why do we worry about whether a company owns the instruction set or not? Well, one big challenge is that companies and their instruction sets come and go. So there used to be a very big and important computer company on the East Coast called Digital Equipment Corporation. And they had some very important instruction sets, PDP-11, VAX, Alpha. But they're gone now. And if you built your software world around these instruction sets, there's nothing you can do. You have to move to a new instruction set now. And it's not something you did wrong. It's something that happened with the business fortunes of the company that owned that instruction set interface you built your world around. Intel, they're obviously still around, very popular, but they've had a lot of instruction sets come and go. i960, i860, Itanium we talked about. MIPS is one of the early RISC architectures. This is an interesting case. They were successful for a while, then had a downturn. They sold to Imagination. Imagination sold them to Wave, a startup. At Wave, they decided they would, inspired by the RISC-V wave, they decided to open up MIPS ISA, but then they decided to close it down again. Spark is another interesting example of an early RISC, one of the first RISC architectures. And actually, this was one of the first open ISAs as well. Back in 1994, Sun made the Spark version 8, the 32-bit version of the ISA, an open standard with the IEEE. And there were a lot of companies building implementations around Spark then. But then later, Sun was acquired by Oracle, and the 64-bit instruction set was closed up. And then finally, Oracle just closed down all of Spark development completely. ARM is a big, powerful company now in embedded processing. But there were some shockwaves when they were sold to SoftBank, taken private. So now they're a privately run company. And so, people are worried about what will happen to the future of this ISA now. So basically, companies and their ISAs come and go. And if you tie your software stack to this proprietary instruction set, you'll have to face the fact that maybe in the future, due to something outside your control, you'll have to move your instruction set and move all your software. Now, it's not only that there are a lot of different companies providing ISAs. Even if you look at a single chip, a single SoC today, you'll see there are many instruction sets on that single SoC. As well as the applications processor, which is usually ARM these days, you'll see there is graphics, image, radio, audio, security processors, power management processors. And it's not unusual to find over a dozen different instruction sets on a single chip. And each of these will have their own software stack. So why are there so many? Well, one reason is that the applications processor instruction set wasn't really designed as the basis for an accelerator or one of these specialized architectures. And as a result, it's just too big and it's not a good choice to base these other ones around. Second, even if you wanted to, you wouldn't be able to because of the licensing terms. So when somebody assembles an SoC, they license IP from many vendors, and each of those vendors is not able to use one of the proprietary standard ISAs when they design their own IP. And so they design their own ISA because they need to. And one of the worst things that can happen also is when you're building this SoC, the engineers of your company may decide they should just go build their own ISA for one of the cores on the chip, which then means they have to support the software for that core for all time afterwards. So do we really need all these different instruction sets? And do they have to be proprietary? And do they have to keep disappearing? What if there was just one stable, free, and open ISA everybody could use for everything? And that's really the premise behind RISC-V. Why don't we just have a single one that can serve all these purposes, that's not owned by anybody, and everybody can use for everything? So the genesis of RISC-V really was back in our research group in Berkeley in 2010. We've been doing a lot of research projects and needed a new ISA to base the next set of projects around. We took a look at industry, and the obvious choices at the time, still today would be maybe the obvious choice, x86 and ARM. And the issues were that they were just impossible to use. For one thing, they were very complicated, and we wanted to build very simple, efficient implementations with a small team. Also, there were the IP issues. We wanted to build cores and share this with the community, open source the implementations, but it would not be possible with these instruction sets. It's simply not legally possible to share implementations of these ISAs. So we decided to do our own clean slate ISA. We thought it'd be a 3-month project. I'll give a shout out to the principal designers, Andrew Waterman and Yunsub Lee, who were graduate students at the time, and my colleague, Dave Patterson. We were the main designers, but many people helped us out along the way in designing the ISA. After 4 years, the 3-month project actually took more like 4 years, but we had a frozen spec at that point, and we'd done many tape outs and ported software and iterated on this many times in the meantime. So it's called RISC-V, pronounced RISC-V, because it's the 5th major Berkeley RISC ISA. So going back to the original RISC-1 and RISC-2 projects from the early 80s, Dave Patterson always regrets not keeping the brand. So we went back and posthumously renamed the SOAR and SPUR projects RISC-3 and RISC-4, and that's how we got to RISC-V. And note it's RISC-V and not RISC-V, because the first 2 projects were RISC-1 and RISC-2, not RISC-I and RISC-II, right? So we were working on this ISA, that we started getting external emails from people asking about the instruction set and wondering why we're changing things around. Then we realized there was external interest in this project we've been doing. So at Hot Chips conference in 2014, we made this major promotional push where we all dressed up in these blue t-shirts and promoted the idea there should be a free and open instruction set. We had an amazingly positive response at Hot Chips. And many people from industry told us this was something they really needed out there. There really was a big hole in the market for an open instruction set. But one thing they said was it cannot stay just a university project. we really need a more stable home for something if we're going to build industry around this. So in 2015, we created the RISC-V Foundation to be a non-profit entity to basically manage the RISC-V standard. Now, recently, we've reincorporated the foundation as RISC-V International, housed in Switzerland, to really reinforce the message that RISC-V is intended as a global standard. So to give you some examples, in China, many members, a lot of interest, both in industry, academia, in using RISC-V. In Europe, oops, sorry, let me go back. China and Europe, the European Process Initiative recently announced they've declared RISC-V as a key architecture that will be used to build high-performance computing accelerators to use in HPC systems. In India was actually one of the first countries to seriously adopt RISC-V, and they funded a number of projects, including at IIT Madras, the Shakti project, which is developing 6 open source RISC-V processors that can be used by anybody. Japan, we've seen increasing momentum, many more people showing up at the events in Japan. And here in North America, widespread industry adoption, and already we're shipping millions of cores using RISC-V. For example, every NVIDIA GPU right now is shipping with RISC-V cores in there. Western Digital announced they will move their entire product line to RISC-V. And there's many other companies providing RISC-V cores and selling them inside the US. Now, one thing that may surprise you is the biggest RISC-V event we've had so far was actually in Lahore, Pakistan. And this is actually a photograph of the audience. I was giving a talk at the time, over 3,000 people attending to learn about RISC-V. It's really seen as an enabling technology all around the world to help everybody build up their own indigenous computing technology. Now, it's not just academia and researchers and hobbyists playing with RISC-V. Almost the entire industry is very seriously approaching RISC-V. This is sort of scatter plot of the different members we have. And I'll point out that we have nearly all the major semiconductor companies and vendors are involved in RISC-V. We have IBM, Google, Qualcomm, Samsung, NVIDIA, you name it. Almost every company who's working in this space is interested in RISC-V. And the growth in the membership has just been incredible over the last few years. So how does RISC-V work? So I'll just quickly describe the RISC-V ecosystem. So the center lies RISC-V International, so that we maintain the specifications and manage the interface between software and hardware. Now on the hardware side, it's an open specification, and often people mistakenly say that RISC-V is an open source project. That's actually incorrect. RISC-V is an open specification. But because it's open, it means you can have open source implementations. And there's a great variety of open source cores available for RISC-V right now from many places. But it's not only open source cores, there's also commercially licensed cores available from many vendors. And these vendors are distributed around the globe. For example, Alibaba is in China, Andy's in Taiwan, Codasip in the Czech Republic, Quartus in France, Incor in India, Sci5 in the US, Syntacore and Cloudbearer in Russia. So already today, RISC-V has more commercial core IP providers than any other instruction set in history. And as well as open source and commercially licensed cores, companies are also free to build their own in-house cores. This, for example, is what NVIDIA is doing on the GPUs. They build their own RISC-V core for their own internal use. Now, similarly, on the software side, RISC-V is being adopted upstream as one of the main architectures in many of the open source projects. But it's also being supported by commercial software, commercial licensed software from vendors like Larabac and Sega, IR, etc. They're all supporting RISC-V because of the demand from industry for these same tools. And so really, RISC-V is this specification. It's an open specification that enables open source, but it's also being supported by commercial entities also. So what's different about it? We made the ISA very simple. We made a very clean slate design, learning from the mistakes of the past. We made it very modular. So remember, there's a lot of accelerators, domain-specific cores on these chips today. We wanted to make it, you only included the pieces you needed for each of those applications. We made it stable. We have no commercial interest to keep upgrading it. And so around the community, we have a motivation to keep parts stable and not change them unnecessarily. And finally, it's community design. This is the big difference. We rely on a wide range of experts out there to engage with us to develop all the parts of the ISA, including the software community. And here's just a scatter plot of some of the different working groups that are right now working on enhancing the specification. It's also being a big factor in education. We're seeing a big uptake. It's a natural one for schools. It came from schools. Part of the reason for the design being so simple, it means you can teach the whole ISA in one lecture and teach an implementation in another lecture. It's meant to just quickly get people on board, learning how to do this. So why is it so popular? I think it's important to sort of stop and pause here. Often when I talk to engineers, they sometimes don't see the forest for the trees. The RISC-V movement isn't happening because some particular benchmark ran 10% faster or some implementation was a bit lower power. The movement's happening because this is really a new business model that changes everything. So prior to this, when you were building a chip, you would first have to go talk to different vendors, have them compete. When you picked a vendor, you got their instruction set. This turns it around and says, first you decide, I'm going to use RISC-V. And then you can go out and choose either to pick a commercial core from a vendor or use an open source core or build your own core. So you have that freedom of choice now. And also when you go to build a second generation of your chip, you again can go out to the market. It makes it a very competitive market for processor cores. Also because effectively everybody has an architectural license. We designed the ISA to make it easy to add your own extensions without getting permission from anybody in a way that still lets you run almost standard software. Now you may pick and poke at RISC-V and say, well, I can't find this implementation level or this kind of feature. But basically things are moving so fast that whatever's broken and missing in RISC-V will get fixed. And we're working very hard to fill in the whole ecosystem. So our modest goal at this point is really become the industry standard ISA for everything. And we're pretty far along in that goal. So this event, I think one of the questions I'll get at any open source event is, where are the dev boards? We're desperate to work on RISC-V, but there's no hardware out there. A while back in 2018, we released Hi5 Unleashed from Sci5, which is the first dev board. This is a very limited production run, unfortunately sold out. Also, the chip was quite limited in terms of peripherals, but we saw the impact this had in the open source community that, for example, this shows how fast Debian could port packages over to RISC-V once we released this board. And the other part about the board, because it was so limited, you needed a very expensive expansion board supplied by Microsemi to give you all the peripherals you needed to make it a full-blown PC based on around RISC-V. And this is far too expensive for most people, but this was early days in the first dev board. I just want to close out here by saying, well, there's some relief coming. We have a new dev kit coming from Microchip, who's now the owner of Microsemi. They bought Microsemi. And you can view the chip they're building as including the FPGA and the hardened Sci5 cores together on one piece of silicon. This enables them to make a much lower cost dev board that will have a lot of peripherals. And the good news is that that board is actually coming out. They'll be able to sign up right now at the end of this month, end of July, you'll be able to sign up, and it should be available and shipping by the end of August this year. And so this will give you a much cheaper dev board for working on RISC-V Linux. So I'm excited to share that. And just to conclude here, so RISC-V is really all about maintaining an open ecosystem. And really the important thing here is completing this innovation cycle. By having an open standard, we can use in education. Students can take that knowledge, go straight to industry, apply it to real industrial cores. And then if there's problems in industry, we can feed those problems directly into research. The research solutions are directly applicable out to industry. And this really, I think, is the key, is keeping this innovation cycle going. And that's really the strength of RISC-V. So that's it. And thank you for listening.
Thanks so much. It's good to see that those dev boards are coming out. Like, where can folks go get information on those dev boards again?
Yeah, it's a crowd supply. You can sign up at crowdsupply.com, and you can sign up right now to be put on the list to get information. And as I said, by end of August, they should be shipping, I hear, from Microchip.
All right. Hopefully people will be out and about more than they are today, but I bet people are just itching to get a hold of those dev boards in particular while they're sitting at social isolating. So I look forward to seeing those come out in August.
Okay, thanks.
All right. Thank you. And thank everyone for joining us this week. Enjoy the rest of your day. Enjoy our virtual event, and we will see you back at our next virtual event soon.